Today I'm going to cover the last topic in our blog about rings, Chinese remainder theorem. And this will generalize a couple of constructions that we have already seen in the older V-sets. Let me remind you them. So recall that I asked you to prove that R x quotient by the ideal generated by x squared minus 1 is isomorphic to the product R cross R. And another example that we can consider is Z mod 12Z. And we can prove that it is isomorphic to Z mod 4Z times Z mod 3Z by sending 1 to the pair of the class of 1 modulo 4 and the class of 1 modulo 3. Then we can see that under this isomorphism, minus 3 will go to the class of 1, 0, is also 9. And this is because 9 modulo 4 is equal to 1, and 9 modulo 3 is equal to 0. And similarly, the class of 4 goes to 0, 1, because 4 modulo 4 is 0 and 4 modulo 3 is 1. And a more general phenomenon is this Chinese remainder theorem, which says that if we have a unique factorization domain and a number of elements, n1 through nk in R, that are pairwise co-prime, non-zero, then we can conclude that R modulo the ideal generated by the product of n1 through nk is isomorphic to the product of R mod n1 cross R mod n2, etc. till R mod nk. In order to prove this, I will first formulate a lemma which will seem a bit more general than this statement. But nevertheless, I will use this lemma to inductively get this isomorphism by splitting n i's one by one into this product. First, I need to give a couple of definitions. So let's say that we have two ideals in R in any ring, in any commutative ring. Then I can define the intersection of ideals as a set theoretic intersection. I intersect with j is equal to the set of elements I, such that I belongs to both I and j. And this is also an ideal, because I plus sub-element j from the intersection would belong to both I and j because I and j were ideals. And this proves that the intersection is closed under addition. And similarly, we prove that this set satisfies the multiplicative absorption property. And therefore, it is an ideal in R. Then a warning that in general the union of two ideals is not an ideal. For example, we can take the ideal generated by 2 and the ideal generated by 3 inside the ring of integers. Then 2 plus 3, which is equal to 5, does not belong to this union because 5 is not divisible by neither 2 nor 3. So this set is not closed under addition. So this union is not an ideal. But if we say that we want to generate the ideal by the elements from both of these ideals, then this will become an ideal, and we call it the sum of two ideals, I plus j. And it is defined as the set of elements of R that can be written as I plus j, with I from I and j from j. And this set will be an ideal in R. By this form, by the definition, we see that it is closed under addition. And if we take any element R in R and multiply this sum by this element R, then by distributivity, we get this sum, and we see that Ri is inside of I because I is there, so it belongs to I, and Rj belongs to j similarly, so again we have an element of the form, an element from I and an element from j. And so we observed both properties, both defining properties of the ideal. And the last definition is the product of two ideals, I times j. We usually don't try anything between two ideals to denote the product. It is the set of all sums an times in times jn, and the sum is finite, so n goes from 1 to n, where n is some natural number an is any coefficient from R, in is in I, and Jn is in J. Or equivalently, we can say that Ij is the ideal generated by elements of the form Ij, where I is inside of I, and J is inside of J. And again, a word of warning that in general, the set of elements of the form Ij, where I is in I and J is in J, is not an ideal. Because here, the closeness under sum would not be automatic. For example of this phenomenon, let us consider the ring in 4 variables, k of x, y, z, w, where k is a field. Then, if we take the first ideal to be x, generated by x and y, the second ideal is z, w, then their product is the ideal generated by xz, xw, yz, yw. So it is enough to, so for generators, it is enough to take the product of the generators of this ideal, of these ideals. And we see that the element xz plus yw lies in this product, but it is not of the form Ij for some polynomial I and some polynomial j. And this is because the degree of I is at least 1, the degree of j is at least 1. So this would give a non-trivial factoring of this polynomial, but you proved in one of your homeworks that this polynomial is irreducible. Okay, and you can observe that for any choice of ideals, I and j, the product of I and j always lies inside the intersection of I and j. And this is because if we take any element of the form I times j, because I lies in I, this product lies in I, and because j lies in j capital, this product lies in j. So elements of this form lie in the intersection of these ideals, and they generate the product ideal. therefore, this whole ideal lies inside I intersected with J. Lies inside, so products are contained in the intersections. And let us consider some examples. So take R for Z. Then we can see that if we take both I and J to be equal to the same ideal generated, so let's say by element 2, then the product will be the ideal generated by 4, because we multiply these generators and get 4. And this belongs to the intersection of the ideal generated by 2 with itself, which is 2, but it is not equal to. So this is not in general an equality. However, sometimes it is. So if I take 2 and multiply it by 3, then I get the ideal generated by number 6. And this is also equal to the intersection of the ideals generated by 2 and by 3. And this is because ideal generated by 6 consists of numbers divisible by 6, which is the same as being divisible by 2 and being divisible by 3 simultaneously. And now let me formulate a lemma. If I and J are ideals in any commutative ring R, then for a homomorphism phi from R to R mod I cross R mod J that sends an element R to its equivalence class mod I and equivalence class mod J. For phi, its kernel is equal to the intersection of these ideals. And this is the first step in the formulation of the Chinese remainder theorems for ideals. But I'm not going to go as far, and you can probably figure out it on your own. But instead, I will derive an induction step for this theorem. So, for the proof, let's take an element R in the kernel of phi. Then phi of R is equal to 0. And this is equivalent to saying that both of these classes are equal to 0 in their respective quotient rings. So R is equal to 0 in R mod I, and R is equal to 0 in R mod J. By the construction of the quotient ring, we know that R equal to 0 in R mod I means that R is an element of I. And similarly for this part, we get that R is an element of J. And this is exactly the definition of the intersection, of set intersection. So it means that R belongs to the intersection of I and J. And so we proved that whenever we take an element in the kernel, it lies in the intersection of these ideals. And conversely, if R is in the intersection of these ideals, we can follow the sequence of these equivalences in the other direction. So R belongs to both I and J, which means that R is equal to 0 in both quotient rings. And this means that this pair is the 0 pair in the product of the quotient rings. Conversely, if R is in the intersection, then R also belongs to the kernel. And a corollary of this lemma is as follows. If R is a unique factorization domain and M and M in R are non-zero co-prime elements, so their GCD is equal to 1. In this case, the quotient ring R mod the principal ideal generated by NM is isomorphic to R mod N times R mod M. For the proof, we define a homomorphism P, like here, from R to the product, R mod M times R mod M. Then by this lemma, we get that the kernel of P is equal to the intersection of N and the ideal generated by M. But now let us use the assumption that N and M are co-prime elements, which means that if both N and M divide some element R, N divides R and M divides R, then by coprimality, their product M also divides R. So from this observation, we get that the kernel of V is the principal ideal generated by N and M. And by the first isomorphism theorem, the image of phi is isomorphic to R mod and M. And so we proved that there is a certain subring, which is the image of phi, inside this product ring. And we need to show that phi is surjective, which would conclude the proof of this isomorphism. For surjectivity, it is enough to show that element of the form 1, 0 belongs to the image of phi, and element of the form 0, 1 is in the image of phi, because then to get any other element of this product ring, we would multiply, we would take a linear combination of elements from their preimages and get any element of the form and get any element of the form R1 R2 as R1 times 1.1, 0 and R2 times 0, 1. Okay, so now for surjectivity, let us again use that n and m are co-prime. And this happens when the greatest common divisor is 1, or equivalently, if the ideal they generate together is the unit ideal. And that is equivalent to saying that there are elements x and y in R, such that xn plus ym is equal to 1. Then let us evaluate phi at xm. It is equal to the class of xn mod n and xn mod m. And since xn is divisible by n, this is equal, the first coordinate is equal to 0. And here we see that xn modulo m is equal to xn plus ym modulo m. And this is equal to 1, so we get 0, 1. And also phi of ym is equal to 1, 0. And any element of the form R1, R2 is in the image of phi of R1 times the preimage of this element, and R2 times the preimage of this element, this element, x. And so phi is surjective. So the image of phi coincides with the whole ring and is isomorphic by the first isomorphism theorem to R mod out by the product of nm. And so we get the desired isomorphism. And now I can show you how I apply this intermediate result to conclude the Chinese remainders theorem, proof of Chinese remainder theorem. Observe that since the elements n1 through nk are co-prime, we also have their pairwise co-prime. We also have that n1 and n2 times ... nk. These two elements are co-prime. And now we are in the situation of this corollary. So we conclude that R mod out by the product of all these elements is isomorphic to R mod n1 times R mod n2 through nk. And then further we can, in the same fashion, split out R mod N2, because we use the same logic that N2 is co-prime to the product of N3 through Nk. So we get R mod N1 cross R mod N2 cross R mod the product of N3 through Nk. And by induction argument, so we could have said that since this has a smaller number of elements, we can use induction argument to conclude that this is also equal to the product of rings where we mod out by just one factor. R mod N1 times R mod N2 times etc. through R mod Nk. But note that we used coprimality to prove this corollary, and it is an important assumption because let's see that again in the example of Z mod 12Z. It is isomorphic to Z mod 4 cross Z mod 3 Z, because 4 and 3 are two co-prime factors of 12. But we cannot write that this is Z mod 2 cross Z mod 2 cross Z mod 3. And you can see easily that this can never be an isomorphism, because this ring has characteristic 12. And this ring has characteristic 6. Because if we take element 1, 1, 1, we sum it up together with itself 6 times, and we get 6 mod 2 is 0. Here it is also 0, and 6 mod 3 is 0. And two rings of different characteristic cannot be isomorphic.